Okay, so if you, I haven't posted yet. Sorry. Cool. If you look at the schedule here, scroll down to the bottom of the syllabus, you'll see the schedule. The pace is super fast. I'll tell you, when I taught Circuit 1 at Phillips College, I spent a week to teach operational amplifiers. Here it's just like two lectures and 15 minutes for each. And for nonlinear circuits, it usually take 3 weeks. So the capacitors and inductors were only like 2 lectures, I think. And if you, since you guys have been in the class for almost 2/3 of the semester, you find out there's no such a feedback mechanism. So you did the homework in tutorials and homework on in Canvas, but there's no way that I can still see it, but I'm not returning it back to you to let you ask questions in the class. So it's sort of like we are disconnected from each other. That's not the right way to teach. But the problem is a very big section. If I can manage everything I can teach in the class, what I'm going to do, I will give you very short quizzes. For example, just to have a box and with a plus and minus sign on each end, and then let you tell me it's absorbing or delivering power, right? Very simple, like 5 minutes quizzes every Friday or Wednesday, and you give it back to me. I can grade it. I mean, 100 quizzes, everyone probably only take me like 3 seconds. I'm willing to do it and return it back to you. So I can know your names. I know each one's name. So you know that if you're not here, I will know you are not here, right? You are absent. So you will come, and which will push you or motivate you to learn. Another thing is, through that feedback, you know why you did it wrong. I will go through the problem in the class, so which will improve your knowledge as well. But now the case is, throughout the past few weeks, I just keep rushing and rushing. I don't even have 1 single minute to talk about anything else. So what I can do is just basically go through all the homework assignments, and I couldn't even finish all the problems in the class. You probably already realize that. I just don't have any extra time. So, and now we are still like 2 lectures behind the other section. How could you imagine if I just go through slides, if I just use slides, no calculations at all? I mean, could you still finish all the homework assignments easily after class? It might be even more difficult. So I went through almost every single problem in the class. I tried. If I couldn't finish, I even recorded lectures and posted after the class, right? I hope that helped, but the thing is still there's no feedback. So I'm pretty sure a lot of students are, getting frustrated because they're not getting feedback. So my plan is, I'm not trying to add pressure, but on Fridays, I'm trying to give you, another thing. So I was trying to add a quiz, but the thing is I cannot. I'm not allowed to. Is that interesting? Your teacher are not allowed to do the things are right. And I ask other sections, I say, if you want to do that, we have to keep all the sections the same. We have to do the same to keep it fair, because they want other sections to have the bonus points as well. In that case, they have to shift the schedule in the syllabus, delay it for another week. I have to make a big change to it. I don't have intention to change anything for other sections. I just want to build a connection between you and me. So what I'm going to do is, so they cannot be counted as bonus points. I just cannot do it. I'll still give you 5 minutes quizzes, but why you are motivated to do it? Like you have the question, why do I have to do it, right? So what I'm thinking is, these little problems will be very similar to the problem in the exams. So for example, there are like 20 problems in the exam. I'll take out let's take baby steps. I'll take problem 1 and look at that problem, find out the key point, the key knowledge you need to know. I'll extract that information and put in the quiz on Fridays. So you are not losing points, it's not counted to a grade, it's not a bonus point, but however, you learn it, so it's contribute to your final exam or exam 2. And I will be able to give you feedback. Maybe let's just, it's a 5 minutes quiz, and I will probably return it back to you and let you know what's going wrong for another 5 minutes in the class, so we don't have to shift all the schedule for like 2 weeks or 1 week. I hope that helps. I don't mind to spend another like 30 to 40 minutes to grade it and post the grades, as long as it helps. It's only 5 to 6 weeks left. I try to do the best to help you guys. However, just remind you, starting from today's lecture, it's getting hard, getting very difficult. But I already tell you, if you follow, see how many pages? I'm already summarized on the paper. 1, 2, 3, just 3 pages. If you can do these, you just spend the time after the class, derive it by yourself. I already summarized all the cases. Even though you look at the problems in tutorial 8 and homework 8, all different types of problems. If you know how to do this, it solves like 99% of the problems over here. Trust me. So if you cannot manage this, go home and derive every single thing like what I'm gonna do in the class by yourself. After that, you'll be good. It's the same to me. I was not able to do this when I was in undergraduate as well. You know, I summarized everything when I have to teach it. since I have to teach it, right? All right. Do we have Marilyn Stephens and Alexandra Stephens here now? No? Okay. So if you don't understand how this transient analysis works, it's ugly and it's a monster. But if you know how that works, it's beautiful. It's connecting to digital circuits. I'll let you know why and how, okay? Very useful stuff. If you have the circuits only have like resistors and power supplies, is boring, right? We need the inductors and capacitors in there. All right, so first of all, what you need, so first the model you need to know. It's called natural response. Natural response. Ask questions whenever you have any questions, right? Don't hesitate to ask any questions when I'm going through all these problems. It's called natural response. First model you need to understand, the simplest one, the easiest, first step. So what does that mean? I'm going to draw the little schematic here really quick. So for example, I have a capacitor, has a, let's say VC0 initial voltage. So sometimes you'll see a superscription on the top is a minus, which means it's before time 0. It's right before time 0. That one, for example, is 5 volts. And a discharging through a resistor. And there's a switch. Sorry, I forgot to draw that. At T0, you close the switch. Initially, the capacitor stores 5 volts on it. So at T0, you close the switch. What's going to happen? It's going to discharge the cap. Why this performs different from the power supply module, like a voltage source? What's the difference? You close this. If you have a voltage source here, right? You close the switch at T0. What's going to happen? What's going to happen? It's just supplying voltage to it, right? It's going to run current through the resistor. But the difference is this guy has a finite amount of charges, but this one doesn't. Since this is a power supply, if it's a benchtop power supply, it's plugged into the wall of the outlet. It's directly connected to the power plant. Infinite amount of charges. So it's going to keep going, no difference. But this is attenuating. This is attenuating because it's a floating, it's called a floating. Why it's floating? Float. It's very important to understand these kind of models. It's a floating source, right? It's not being supplied by an infinite source. So this is a finite amount of charges will be discharged over time. So now our job here is trying to find out the VT over time. So that's what we are doing now. Okay. Why we should do that? Because we are curious. You got the voltage across it. You want to know how the voltage varies over time. That's why we need to know that. So that's the first case, the easiest case, which is just simply discharging it. It's called natural response. It's naturally discharging itself. Okay? Now let's derive it. So you'll see circuits looks like this. However, eventually, just the discharging, it's just a model like this. But I'm going to draw something like you'll see in the homework assignments, right? Plus and minus VCT R, and here's a switch at T0. You switch it here, okay? So this is Vs, is the source, and that's the source resistance Rs. Are they the same problem? It was charged up. So before T0, it's been connected to the source for a long time. Let me ask you a very quick question because it's important to understand this before we move forward. So before I switch it here, it's the capacitor is already connected to this voltage source for a long time. What is the voltage stored over here? Vs. It's been a long time, 100 years. So this is gonna store Vs. Okay? So if I switch it here, what's gonna happen? Gonna discharge. It's called natural response. Okay, so we are trying to find out the natural response of the capacitor. Same thing. I close the switch, capacitor is going to discharge over the resistor. Same stuff. So you can see all variants of circuits like this, but you need to know what is this problem is asking you to do. So for this type of problem, you should know that it's natural response. So now let's derive it. Just look at this one, okay? So the circuits here will be eventually this. So at T at 0 plus. So now you'll see what 0 plus means. So 0 minus means before you switch it. 0 plus means right after you switch it to here. So at 0 plus, you got a circuit like this. So it's asking for VCT, okay? So what's gonna happen? It's gonna discharge it. So it's basically discharging over here for the physical current. It's gonna run that way. But the thing is, remember how we model the capacitor's currents? Doesn't matter, just the direction of it, right? So we model this way, and that current equals what? C dV dt. So if you were not here last week, I want to let you just to memorize this for now, okay? Since we talked about this last week. Okay? The current of the capacitor is being modeled like this. The current flowing into it is C dV dt. I'm going to repeat it for 100 times until you can remember, can master it. C dV dt. Okay? All right. So the current flowing into it, which is here, right? Same thing. It's going to create a drop. So how do we list the equation? What kind of law you want to use? KVL. Starting from here, you see a plus first. So what's the current? ICT, right? Times what? R, which is the voltage here. Plus what? VCT. Equals what? 0. KVL. Okay? What is ICT? C dV dt. Do you need to worry about this current? Not right now. We just want to list the equation and calculate VCT. Why do we have to worry about this current, even though this is the physical current running in the circuit, because it's discharging through it, right? We don't have to worry about that right now. It's just, since it's just one branch, if ICT is C dV dt, the current going through this guy from left to right will be C dV dt. Exactly, it's the same current. What's next? So move things around. So we are getting RC dVc dt over dt equals minus VCT. Moving forward, we are getting, so move VCT over here, moving dt and RCT to the right. So it's RC 1 over RC dt equals VCT 1 dVCT. Okay? And integrate on both sides. From 0 to t, from 0 to, VCT. So this becomes natural log of VCT equals minus T over RC. Do this on both sides. We're getting VCT equals E minus T over RC. Wait, are we losing anything? Sorry, here's V0. Starting from V0T to VCT, okay? That's the initial voltage stored on it. So, let's delete this one. I'm moving here. So we're getting natural log of VCT minus natural log of VC0, VC0 here equals minus T over RC, and this is natural log of VCT divided by VC0. VC0 makes sense, right? Because VCT at the very beginning is VC0, which is the initial voltage stored in it. As a natural response, the capacitor has an initial voltage in it, and now it starts discharging. So here equals minus T over RC, and that becomes VCT over VC0 equals this. So VCT, here we go, VC0 times, that's a natural response equation here. You want to know. All right? What is this? That's the initial voltage stored in the cap. What is this? That's attenuation factor. Attenuation factor. Why? Because that's the E is 2.7 something, right? So E to the minus something power, which is actually, the curve looks like this. It's attenuating naturally. It's called natural response. So that's why it's attenuating naturally. Why it's naturally? Why it's called naturally? Because no force. You close it, the cap is manufactured that way, right? So it's naturally discharging through it. There's no other forces or sources being added to it. It's just the discharging by itself. No interference from anything else. So it's attenuating that way, okay? So VCT is a constant. Oh, VC0 is constant. Initial voltage stores in it. So one constant times this one, it's going to attenuating this curve that way, right? So that's how it discharges itself. This is called natural response. Any questions on this before moving forward to the step response, which is more complicated? Super important. Any questions? What's that?
So C's are the capacitance, right?
Yeah, the capacitance. Oh, this is a subscription here. Subscript.
Gotcha.
VCT, yeah.
Oh, so just
Yeah. VCT is a VT. We call it VT, but VC. It's not V times C, all right? It's a VCT. Okay? Can we moving forward? Can we move forward to next? You are already 40% done for all the things you need to know, okay? Not too painful at all, right? By far, it's good. Okay. So before we do inductor's natural response, let's do finish all the capacitor stuff first because it's very similar for the inductor as well. So the next one is called step response. Or sometimes you'll see it's called forced response. Here's a typical circuit for you guys. It's not one of the problems you can see in the homework assignments. This is something I designed without a patent on it. VCT. What's the difference compared to the previous one? What's the difference? Here, the previous one has a what here? Wire. But now after you switch here, you get another source. It's trying to complicate things, right? The T minus 0, no difference, right? T minus 0, I'm going to draw it for you. Okay, that's T minus 0, T0 minus. Okay, and T0 plus becomes this. VS2 so at T 0 minus, when T is 0 minus, what's the voltage across the cap? After 100 years, what's the voltage across it? VS1. So VS1 is what? VC what? 0 minus, right? What about this? Right after you close it, can you get a voltage here across it to be VS2 immediately or instantaneously? Can you? Why? VCT equals what? VCT is this. How could you get a voltage exactly to be this without infinite current? You need an infinite current to get the voltage immediately to this value. But do you have infinite current existing? No. It takes time to integrate. So it won't be VS2 immediately. So you have to derive VCT. It's going to be something over time. How do you do it? K what? L. Yeah. KCL, right? Okay. What does the equation look like? I'll start a new paper. It's okay. You pay the tuition. Let's do it. Still have a lot of time, which is good. Minus VS2 what? Plus what? Remember how do we model the current in the cap? ICT equals what? C D V dt. Alright? R times what? C D V C T dt. That's ICT, which is the same current running through the resistor as well. Plus what? VCT. What are we trying to do here? Let's take one step back. Half of you don't know what we're doing here, right? What's the goal? You need to know the goal, right? VCT, right? Okay, cool. Remind yourself about your goal. Why do you come to School of Mines? Got a job, right? What's next? RC dVc t dt equals Vs2 minus Vct. All right. Move this to the left and move these two to the right. So you are getting Vs2 minus Vct over 1 over that dVct. That equals dt. I know this is the boring part. All right. So I'm trying to not letting you memorize or put that equation in your on your cheat sheet during the exam, because you will forget it right after the exam. So you have to know how to derive it, even though this is just a linear differential equation. See? Is that a linear differential equation? Did you learn that in Calc 1? So this is like a plus by prime plus y equals 0, right? And there's the equation you have to put on the cheat sheet in order to calculate it. I hate that. So you should know how to derive it very quickly. It's not very difficult. Let's do it. So after the class, you always want to derive it yourself, like I said at the very beginning. So it's going to solve 90% of the problems. Forever, okay? What's next? Integrate it. 0 to t. What about here? VCT. So VCT changes from where to where? From the initial voltage, right, which is Vs1, which is also Vc0. So Vc0 is Vs1, right? To where, eventually? Let's just say VCT. Okay? What's next? Integrate it, right? So on the right is very simple. It's just basically T over RC. No problem. So on the left, I have to change it a little bit. So let's change here first. I'm gonna change VCT to minus VCT first. So the limits has to be changed as well. Does that make sense? So the goal is to have this one the same as this guy, so I can directly use the natural log. So V minus VCT matches. Good. Only has a constant left, so just add to it. Make sense? Any questions? Any questions by far? It's okay, you don't have to memorize it. The longest equation existing in this class, in this lecture. No worries. So next will be very simple because they all match, right? It's the same thing.
Will you scroll up just a little bit? How come the limits on that left integral are negative? Or yeah.
Oh, because I added minus sign over here. Oh, have to do this as well. Because the minus this guy is gonna be minus of these two limits, right? Since you change the variable. So next will be straightforward because you can directly integrate it, which is minus natural log of because it's natural log of this minus this. So that's why it's division inside. Did I skip one step? So let's move this one here. Why not? Do this again. Getting closer. What's the goal? Find VCT, right? So keep VCT, move VCT to the right, and move everything else to the left. Or we switch it, doesn't matter. Done. So now you're 80% done for all the problems, almost. So what's the conclusion here? VS2 is what? V final, yes. So can I write down like this? VS2 is VC infinity. Can I? We are assuming what? We have renewable energy on this planet, right? So the power plant can supply that power forever. Okay? VS2 is V final. Let's look at the circuit. Someone is not getting it. Do you agree with that? VS2 is V final. We switch it over here. We just let it there for a long time. So VS2 eventually becomes V final, becomes the voltage across it. No doubt on that, right? Okay. So, can I write this in this form? VC final plus VC initial minus VC final times attenuation factor here. Equation number 2. Step response. Now you are 82% there. 82% there. Any questions on this before moving forward? What's up?
So if VS1 and VS2 aren't the same, does anything actually change or no?
0 here, right?
Yeah.
So it's going to be the final voltage though,
So nothing.
because it's not contributing to anything.
Yeah.
So what's happening is, that's a good question. So what's going to happen? So you switch here, you switch it here, the same voltage. Why do you have to switch it? Same voltage, no difference. Because it's balanced. You got a VS1, VS2, same pressure, pushing. Right? Like boxing, but same power, right? No currents. There's a special case for this one, makes this beautiful. Let me show you why. Oh, there's another case. So you ask, like, if they are equal, what's going to happen? So that's what's going to happen, right? So this becomes 0, the voltage is going to be the same, and there's no current. So what if I don't have anything over here? No initial voltage. So there was nothing over the capacitor, and I switch it to a power supply. Is that natural response? Ask yourself, is that natural response? What is natural response? We introduced at the very beginning of the class. What is it?
Natural discharge.
Natural discharge. But if I switch, it initially has nothing to discharge, but I just immediately connect it to a voltage source. It's charging, it's not discharging, so it's not natural response. The equation will be different, right? Why it's going to be different? How do I find that equation though? Do I have to go through this again, like take another 15 minutes?
Wouldn't it be forced because it's forcing it to charge? You just treat the V initial as nothing,
Yes. So what you want to put in here?
0.
Yes. All right. Let's see what's going to happen. And everything starts making perfect sense. I'll show you really quick. You'll start loving circuits. Okay. What's next? Oh, this is for VC0 equals 0, right? Okay. What's next? Oh, keep in mind this is called step response. This is called step response. You need to memorize this. You need to memorize it. Because this class allows you guys to bring a cheat sheet eventually, but so please memorize this. And another thing you need to memorize is this guy. It doesn't mean that you don't know how to derive it. I showed you how to derive it. Go home and practice it. But however, you don't want to work on one problem, derive it, another problem, derive it. You don't want to do that, right? Just memorize this, okay? So this is attenuation factor, it's the initial voltage. Initial voltage will be attenuated in this rate. And this is a step response. What's happening? Memorize it, even though it's longer, but memorize it. The final voltage plus the initial voltage minus the final voltage, parentheses, and times attenuation factor. Something you want to memorize, okay? All right. If VC00 is going to be a special case for the step response. So this eventually becomes what? VC minus VC final times E over E to the power of this, and eventually this is VC this times 1 minus the attenuation factor. Ooh, what is this? What is this? This is beautiful. So now by far we have 3 equations you need to know. What are they? First, what's the first one? Natural response. What that looks like? Initial voltage times what? Right? E to the negative t over RC. Attenuation factor. It times it, attenuates it. Okay? So what's the second one we just learned? Step response, the longer one, right? The final voltage plus parentheses, blah blah, times attenuation factor. What's the third one? The special case of the step response. That's it. Everything. 89% already, since we haven't covered inductors as well. So inductors will be the same way to derive it. That's why I'm probably only worth like 10% of all the efforts. It's easy. Same thing. If you know how to do these ones, just change the parameters, will be the inductors. But no, any questions on this? Any questions on this? And here's the important concept. RC, the unit, is time. Resistance times capacitor is the unit is time. So this is called a time constant. Is that called time constant? I forgot the exact name of it. Oh, time constant. Since you see RC is everywhere, it's here, here. So how this is getting defined? Why RC is a time constant over here? So the time constant RC is what? Because E is what? E is 2.7, right? Okay. So this is minus T over RC, because when RC equals so when T equals RC, what's going to happen? You're having 2.7 minus 1, and that's also a constant. So this is somewhere around like 0.3. So when T equals RC, which is a constant, you are attenuating your, this is 0.3, like 6, I think. So you have how much left of the voltage? How much left? 36% left. It's just by definition, okay? So what's the definition of time constant? What that really is? It's the time it takes to attenuate to what? 36% of the initial voltage. Just let you know, it's not that important though. So the time constant is important, but the 36%, the number is not that important. It's by definition. So why is this beautiful? Let me show you one case, okay? This is called RC circuit. RC circuit. When you close it, it starts charging up the cap. So you are wondering why we always involve a resistor and capacitor to form an RC circuit. Why do we do that? For people who are learning circuit 1, you don't have a big picture of the entire field. I mean, you are wondering why we have to do that. Why? Why do we worry about capacitors and resistance? Because that exists everywhere in the circuit. In the chip, very high level integrated circuits, there are just so many, it's called parasitic capacitance. You don't have capacitors exactly over there by design, but since the cables, if you have two cables close to each other, and you have silicon dioxide in the middle, it's forming a dielectric material in the middle. It's forming capacitors. They're called parasitic capacitances everywhere, including the cables, whatever. It's just everywhere. The cables are rubber materials and metals around it, so it's gonna forming caps everywhere along the cable. And we don't have perfect conductors, right? So the cables, they actually have resistance, even though they are very low. So eventually what you have in the transmission lines and everywhere in the circuits, they are basically RC circuits. So what does that mean? So it takes time to charge and discharge. Why that matters? That's the limit of the speed, how you can run the CPU in the computer. So for example, let me show you this RC circuit. If you switch it on, like 5 volts logic in your CPU, you switch it on, what's gonna happen? So this is like, you switch it on, you are expecting a sharp or very steep rising edge, right? You switch it on, you are expecting a 5 volts from 0 to 5 volts immediately. However, that doesn't happen, unfortunately. What's going to happen in real world, in the real circuits? It takes time to charge it up. How that works? It's like, okay? So if all the digital circuits are running like this, okay, that's the real pulses, like 0 and 1s in digital circuits to run clocking your CPU. Can you run the speed of the clocks or the signals shorter than this period? You want to switch it faster than this time? Can you? No, it's not even charging up. You don't want to switch it off before it's charging up since you're not getting a 1. If you want to do this, okay? I want to switch it off. So what's going to happen is it's going to oscillate. It won't be able to charge up to logic 1. You're not getting the real data over there for the computer. So that limits the speed of how you can run the circuits. So, all right. Any question on this? Anything here by far? I think we already covered pretty much almost everything I want to cover. What's that?
In the step response diagram, if our VS of 2 is like a dependent voltage source, is it still step or is that a natural response?
I don't think we have that type of problems, but it's going to be a step response depending on what kind of parameters determine that source's voltage value, right? Yeah. See, if whatever happening after that source is affecting that power supply or no, depending on that. If that one is not being affected by the following circuits, then it should be treated as an ideal source, right? It's still a step response. Yeah. Any other question? Whoever raised your hand? No? So does that make sense over here? So if you have 1 minus this thing, what's going to happen? It's attenuating this guy, right? So you have this curve here. If you have 1 minus, it's exactly this. So it's attenuating. So now it makes sense, right? Why do we want a superconductors? No resistance. No resistance, and then what? You can charge up the cap with 0 time. 0 seconds. You can run whatever speed you want to run the computers. Superconductors. All right. Oh, another thing you need to know before you go through all these problems. So these problems over here, it asks you. Oh, I probably have to record a lecture regarding inductors after this class, so you can work on these problems. But whenever you switch to a circuit like, so for example, VS2. So this VS2 is very simple, right? It's basically just having one resistor here. So what if you have something different? So at T0 plus, you are getting a circuit like this. What's going to happen? R1, R2, R3, R4. At T0 plus, it's getting a voltage here like VC, let's say 5 volts. Okay. It starts discharging, right? Doesn't matter, it looks like this or something else. So how to determine the resistance? Why do you need the resistance? Because you need to know RC, right? All the equations, E, right? VC0. You need to know the R. So what's the way to find R? It's adding more pain to you guys who still cannot master Thevenin's equivalent resistance. It's all adding together. So I'm here to help. Hopefully this can reduce the pain to some extent. So what's happening here? I have to find out the equivalent resistance. You'll see the problems over here a lot to ask you to find out the equivalent resistance. What's the equivalent resistance? You are looking, it's from the capacitor's view, right? You are removing the capacitor as a load, and then you look back. So have an imaginary current going through it and see what's the equivalent resistance is over here. So what's the RTH here? What's the RTH? So this R has to be RTH, just let you know. So what's the RTH? We're not looking backwards, right? No, this is a load. We're looking that way. R1 plus what? R3 plus R4 in parallel with. Okay, so that's how you determine R. How do you determine C? Yes, same thing. If you have, C is just over here, right? Just itself. So what about VC0? Usually it's given. So for natural response is easy. For step response, you don't have too many other parameters. How to determine R? Same thing, equivalent resistance. How to determine final voltage? You just find the static voltage, draw the circuits, and find out that terminal voltage over there. That's the final voltage. How to find the initial voltage? It's usually given. Okay? How to find the initial case? No initial voltage. Then that becomes this guy. All right?
If in the next separation, if you had a resistor before it hits the switch, would you use still RS1 or would you use whatever the resistor factor is?
I'll look at it. I'll solve it.